Welcome dear learners. We are studying quantum chemistry. In this module, we focus on time dependent wave equation. The contents of this module are introduction, Schrödinger quantum mechanics, Schrödinger wave equation, time dependent Schrödinger wave equation, propagation of matter wave, and setting up of time dependent Schrödinger wave equation. Introduction. Louis de Broglie suggested that particles have wave-like properties characterized by a wavelength. And in order to illustrate the particle nature and wave nature of particle, de Broglie derived an equation called de Broglie relation lambda is equal to h by mv, where m is the mass of the body, v is the velocity, h is Planck's constant, lambda is the associated wavelength. So, de Broglie suggested that particles have wave-like properties characterized by wavelength lambda. This idea of wave character of particle inspired Schrödinger and Werner Heisenberg. They independently formulated quantum theory in 1925, and this was to study the behavior of microscopic matter. Now, two types of quantum mechanics proposed by Erwin Schrödinger and Werner Heisenberg are shown here. Erwin Schrödinger proposed wave mechanics. It is based on partial differential equations. However, Werner Heisenberg proposed the quantum mechanics named matrix mechanics, and it is based on matrix method. So, we have Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics. At first, these two approaches, that is wave mechanical approach and matrix mechanical approach, appear different. But later, P.A.M. Dirac and Newman showed that in essence, these two formulations are mathematically equivalent. This means Schrödinger's wave mechanics and Heisenberg's matrix mechanics are two mathematically equivalent formulations. Now, Erwin Schrödinger formulated a version of quantum mechanics that was based on purely the waves or wave functions. And Nobel Prize is received by Erwin Schrödinger in the year 1933 for the discovery of new productive forms of atomic theory. Erwin Rudolf Joseph Alexander Schrödinger was his full name and was an excellent, renowned physicist. Schrödinger quantum mechanics or Schrödinger's quantum mechanics. The Schrödinger's formulation of quantum theory is based on partial differential equation known as the Schrödinger equation or Schrödinger wave equation. We know the Schrödinger wave equation is considered as the heart of the quantum mechanics. That much important, this Schrödinger wave equation. Schrödinger formulated non-relativistic quantum mechanics where mass of the body, mass of the particle is assumed to be constant and does not vary with the velocity or speed. That is termed as non-relativistic quantum mechanics. Mass is independent from velocity or speed. Mass is assumed to be independent from velocity or speed. So that type of formulation is put forward by Schrödinger. So it is nothing but non-relativistic quantum mechanics. However, Dirac developed relativistic quantum theory. The Schrödinger wave equation is the fundamental equation of quantum mechanics. I already mentioned that this Schrödinger wave equation is considered as the heart of the quantum mechanics. The solutions to the Schrödinger wave equations are called the wave functions. The Schrodinger wave equation has two versions. They are the time dependent Schrodinger wave equation and time independent Schrodinger wave equation. The version of Schrodinger equation that does not contain time as a variable is known as time independent Schrodinger wave equation. The time independent Schrodinger wave equation can be represented in simplest mathematical form like this: h hat psi is equal to energy into psi. Here h hat is an operator called total energy operator or Hamiltonian operator. It is theoretically equal to minus s cross square divided by 2m del square plus v. The first portion represents the kinetic energy part and the v represents potential energy part. So here there is kinetic energy and potential energy. So h hat is the total energy operator. On operating h hat with psi, we are getting psi back multiplied by a constant, that is E. So this equation is definitely an eigenvalue equation. The eigenvalue is energy. The wave function psi can be considered as an eigenfunction of total energy operator, Hamiltonian operator. That expression, Hamiltonian psi is equal to energy into psi, contain no time variable. Hence, it is considered as time independent Schrodinger wave equation. The version of Schrodinger wave equation, which is a new version or another different version, with the time as a variable, is known as time dependent Schrodinger wave equation. The time dependent Schrodinger wave equation can be mathematically expressed as is cross dou psi by dou t is equal to Hamiltonian psi. So here we can see the variable time, because the left hand side, in the left hand side, we are differentiating the wave function psi of the present system with respect to time. So I s cross dou by dou t of psi is equal to Hamiltonian psi, that is time dependent Schrodinger wave equation, which is the discussion of this module. Now we are telling something about the most important parameter, that is the wave function abbreviated as psi. Schrodinger introduced a mathematical function psi, which is the variable quantity associated with moving particle and is a complex function of the space coordinates of the particle and time. Psi is called wave function. This is because it characterizes the de Broglie waves associated with the particle. The de Broglie relation lambda is equal to h by mv. If a particle is having very low mass, it is having some wavy character. The wave associated with the matter is said to be the matter wave. Psi is called the wave function because it characterizes the de Broglie waves or matter waves associated with the particle. The time dependent Schrodinger equation is used to find the time dependence, how wave function depends on time, the time dependence of the wave function. This is the complete representation of time dependent Schrodinger wave equation. Hamiltonian psi of RT equal to IH cross dou by dou t psi of RT. Here the Hamiltonian operator is h hat RT. That means the Hamiltonian operator depends on coordinate as well as time. Hence, the Hamiltonian operator is marked as Hamiltonian RT. So, the time dependent Schrodinger equation is Hamiltonian RT psi RT equal to IS cross dou by dou t psi RT. This form of Schrodinger equation is used for non-conservative systems where energy changes with the time, and such concepts are highly useful in spectroscopy. In spectroscopy, we are dealing with the interaction of matter with electromagnetic radiation. You learned about various kinds of spectroscopic techniques like NMR, ESR, microwave, IR, etc., etc. In all such spectroscopic methods, we are discussing interaction of matter with the radiation. So, the time-dependent Schrodinger equation is highly relevant as far as various spectroscopic methods are concerned. Propagation of matter wave. A particle like subatomic particle or electron exhibit wave-particle duality, and the de Broglie wavelength depends on its energy. Why electron is said to exist wave-particle duality? We know lambda is equal to h by mv. The mass of electron is very small quantity. Lambda is equal to h by mv. The mass of electron is 9.1 into 10 raised to minus 31 kilogram is the mass of electron. If you are putting the mass in the denominator, the mass is a very small quantity. Then what will happen is associated wavelength of the electron will be very high. So, electron can propagate just like a wave. It is electron wave or matter wave. The Schrodinger wave equation is based on wave-particle duality. Wave-particle duality means for subatomic particles there is considerable wave character, or every particle is associated with some wave character. That wave character depends on the mass. Since the mass is very small, wave character is very high for electrons and other subatomic particles. Such wave-particle duality, dual nature of particle and wave is utilized in Schrodinger wave equation, that is time-dependent Schrodinger wave equation. It describes the propagation of a particle in terms of matter waves. Consider the propagation of a classical wave along x-axis. The propagation of a classical wave along x-axis. Let this is x-axis. This is the propagation of a classical wave. The vertical displacement psi at a given time t is given by the expression psi t is equal to a cos omega t, where omega is the angular frequency which is equal to 2 pi nu, angular frequency of oscillation, and nu is the angular frequency. The cosine form implies psi is equal to a at t is equal to 0. If wave propagates along x-axis with velocity v, then the time taken by the wave to travel a distance x is x by v. X by v equal to time. In this case, the vertical displacement psi of st at any desired position x and at any desired time t is obtained if t is replaced by t minus s by v in the previous equation. Thus, equation 1 becomes psi of xt equal to a cos omega into t minus s by v. Also, we know that omega equal to 2 pi nu, nu equal to 1 by t, and nu v is equal to nu lambda. Thus, we get psi of xt equal to a cos 2 pi into 1 by t minus x by lambda. The value of psi of xt repeats itself at intervals of period t and also at intervals of lambda along the x-axis. Thus, psi of x t plus t equal to psi of xt and psi of x plus lambda t is equal to psi of xt, because repetition occurs at intervals of lambda and capital T. Using a constant k is equal to 2 pi by lambda, where k is the wave number, omega is equal to 2 pi by t. And cos minus theta, we know it is equal to cos theta. We can rearrange or reorganize equation 3 to get psi of xt equal to a cos kx minus omega t. Psi of st is equal to a cos kx minus omega t. This equation can be generalized as psi of xt equal to a into e raised to kx minus omega t. E raised to I into kx minus omega t. The crucial step is to plug in the concept of wave particle duality and translate the classical wave described by equation 5 into matter wave. This is classical expression for wave or classical wave expression, and this has to be tuned or changed to matter wave. For this, use some relations such as energy is equal to h nu or s cross omega and p is equal to s by lambda or sk, or E by S cross equal to omega and P by S cross equal to K. You know, this constant S cross is equal to H by 2 pi known as Dirac. This constant is known as Dirac. Then psi of xt is equal to a into e raised to I into kx minus omega t. This is equation 5 will be changed into psi is equal to a into e raised to I by S cross px minus et, or psi is equal to a into e raised to minus I by S cross et minus px. Psi is equal to a into e raised to minus I by S cross et minus px. Equation 7 represents the wave equivalent describing a free particles moving along x direction and having total energy capital E and momentum small p. Here the wave parameters omega and k have been replaced by corresponding particle parameters such as energy and momentum. Now we are focusing on setting up of time dependent Schrodinger wave equation. That is, by this discussion we are focusing on how to set up time dependent Schrodinger wave equation. That is, the Schrodinger wave equation where time is a variable. The time dependent Schrodinger wave equation applies to a particle where it moves under the influence of a potential that depends not only on the particle's position but also varies with the time. In non-relativistic limit, the total energy of the particle is the sum of its two forms of energy, namely the kinetic energy and the potential energy. Therefore, the total energy can be represented as E is equal to kinetic energy plus potential energy. The time dependent Schrodinger wave equation applies it to a particle where it moves under the influence of a potential that depends not only on the particle's position but also varies with the time. Energy is equal to p square by 2m plus v, where p is the momentum, p is equal to mv, p square by 2m, p square by 2m represents half mv square, that is kinetic energy, and v represents the potential energy. Multiplying both the sides of equation 2 by psi, we are getting a new expression. E psi is equal to p square by 2m psi plus v psi, and I marked it as equation number 3. The expression for a matter wave propagating along x direction and having a total energy capital E and momentum p can be represented as, this expression we previously learned can be expressed as psi is equal to a into e raised to minus I by s cross et minus px. This equation we already derived in this module itself. Differentiating equation 4 partially with respect to x twice and proceed as follows. So we have to differentiate this expression with respect to x 2 times partially. So we have psi is equal to a into e raised to minus I by s cross into et minus px. I am going to differentiate it twice. So first set of differentiation, partial differentiation is performed here to get dou psi by dou x is equal to a into e raised to minus I by s cross et minus px multiplied by minus I by s cross into minus p. Again differentiating, we are getting the second order differential, partially differential part, dou square psi by dou s square is equal to a into minus I by s cross square minus p square into e raised to minus I by s cross into et minus px. On simplification, we are getting dou square psi by dou s square is equal to minus p square by s cross square into psi, or p square psi is equal to minus s cross square dou square psi by dou x square. Psi is equal to a into e raised to minus I by s cross et minus px. Differentiating equation 4 partially with respect to time and proceed to get dou psi by dou t is equal to a into e raised to minus I by s cross et minus px into minus I by s cross into e, that is equal to minus I by s cross into e psi, or e psi is equal to minus s cross square by I into dou psi by dou t, where dou psi by dou t is the first differential of psi with respect to time partially. We have already e psi is equal to p square psi by 2m plus v psi. P square psi is equal to minus s cross square dou square psi by dou s square, and also e psi is equal to minus s cross square by I into dou psi by dou t. It is possible to substitute the last two results mentioned by equation 5 and 6 in equation 3. So, we get minus s cross by I dou psi by dou t equal to minus s cross square by 2m dou square psi by dou s square plus v psi. On rearranging, we are getting the expression is cross dou psi by dou t equal to minus s cross square by 2m dou square by dou s square plus v psi. And this expression, equation 7, is the time dependent Schrodinger wave equation for a particle of mass m and potential energy v moving along x direction. This is time dependent Schrodinger wave equation for a particle moving along x direction. That is, for the x direction, the expression is is cross dou psi by dou t plus equal to minus s cross square by 2m dou square psi by dou s square plus v psi. If the particle is moving in three-dimensional space, that is, we have to incorporate three Cartesian coordinates x, y and z, then the final equation becomes is cross dou psi by dou t of x, y, z and time equal to minus s cross square by 2m dou square by dou s square minus s cross square by 2m dou square psi by dou y square minus s cross square by 2m dou square psi by dou z square plus v psi. On simplification, we are getting this expression is cross dou psi by dou t is equal to minus s cross square by 2m into del square psi plus v psi, where del square is an operator called the Laplacian or Laplace's operator. So, IH cross dou psi by dou t is equal to minus s cross square by 2m del square plus v into psi. Any condition imposed on the motion of particle will affect the potential energy v, which is a function of coordinate r and time t. By knowing the exact value of potential energy v, the equation may be solved for y. Thus, the time dependent Schrodinger wave equation is used to explain non-stationary phenomena such as electronic transition between two states of atoms. That is, the time dependent Schrodinger wave equation we discussed and derived is highly useful in spectroscopic applications. That all about the present discussion on time dependent Schrodinger wave equation. Have a nice learning experience. Thank you.